This is a general 1.0 ton AC that is completely dead. When I supply power directly, I turn the electricity on, and when I press its emergency on-off switch, it does not respond at all. No LED is turning on in any way. Now, first of all, let's open it. The very first thing we will do is check this fuse. If the fuse is blown, then replace it, and it is possible that the PCB will start working. But in this case, there is no such situation because I have already checked the fuse and it is perfectly fine. Now, first of all, I will check it from the backside. So I will turn the power on again. I have turned the power on. Now, first of all, we will check its AC supply. The AC supply is on this side. As you can see, 224 volts are reaching here, which means the fuse and everything else are completely okay. Next, we will set the meter to DC voltage and check its output to see whether this bridge rectifier is producing an output or not. Now look here. We will connect the positive and negative probes correctly, and as you can see, 316 volts are present here. This means that the bridge rectifier is completely okay. Now, in this situation, we will first secure this PCB in one place so that it does not move too much during testing. This technique is useful because it prevents the PCB from moving around and keeps the multimeter from vibrating too much. Now, the next point to check is its SMPS. We will check whether the SMPS is working properly or not. For that, as you can see here, this is its switching IC, and its part number is TNY274PN. It is installed here, and we will check it. Here, pins 5 to 8 are all source pins, and they are connected to ground, while pin number 4 is its drain pin, pin number 1 is its enable pin, and pin number 2 is its bypass pin. We will check the voltage on these pins. First, we will connect the probes to the source and drain and check how much voltage is present. There are 318 volts between the source and drain. In the same way, we will now check the enable pin. At the moment, the enable pin has 6.26 volts. Now, we will check its bypass pin. There is no voltage present here. This means that this SMPS is doing its job and the required voltages are being generated. Once again, we will turn it over. Here you can see two capacitors. This large one is C9, and this small one is C10. We need to check the voltage on both of them. Here is the capacitor. As you can see, this is C9. We will check the voltage across this capacitor. We will connect the probes to both of its pins. And as you can see, the C9 capacitor has 5 volts. In the same way, let's also check C10. As you can see, C10 is installed here. Now, let's see how much voltage is present on it. As you can see, it has approximately 16 volts. This means that the SMPS is working and the voltages are being generated further in the circuit. Now, we need to check a few more voltages. Only then will we know what fault is present here. Since the SMPS is working, I will remove the display for a while because it was making it difficult for me to work. Now we will check whether the voltages at different points are present properly or not. First of all, we will check this IC. This is a hybrid IC. It handles communication, generates the zero crossing signal, and it also receives the 230 volts AC high voltage. So we need to check whether all of these voltages are present properly or not. Now, if we look at its pin configuration, pin number 1 should have 5 volts. Pin number 2 is the RX receive pin, where the incoming communication signals are received. Pin number 3 is the ground pin. Pin number 4 is used for the zero crossing signal. Pin number 5 is the TX transmit pin, which sends the communication signals out. Next, pin number 10 is the line pin, where the 220 volts, 230 volts AC phase is supplied. Pin number 14 is the neutral pin for the 220 volts, 230 volts AC supply. Finally, pin number 18 is the serial communication pin. The two optocouplers connected here handle the communication, and both the input and output communication signals are carried through this single pin. I will power the PCB. The power is now on, and we will set the multimeter to AC voltage. Then, we will check the voltage here. As you can see, 226 volts AC is present here. This means that the voltage is entering this IC. Now, the next thing we need to check is very important because it allows the microcontroller to operate. That is the zero crossing signal. The zero crossing signal must be present for this IC to enable the microcontroller. If the microcontroller does not receive the zero crossing voltage here, it will not operate, because without the zero crossing signal, the microcontroller assumes that the power coming from the grid is not proper. As a result, it keeps the entire system turned off. For this, pin number 4 generates the zero crossing signal, so we will check it. Pin number 3 is the ground pin, so we will use that for reference. As you can see, this is transistor Q1. We should have voltage on Q1, so we will check it here. First, we will connect the probe to ground. As you can see, the ground is present here. Now, we will check its collector. As you can see, 2.739 volts are present here, which is perfectly okay. This means that the zero crossing circuit is working because 5 volts are not generated here. Instead, the multimeter is showing the half cycle, which is why 2.7 volts is perfectly normal. This means that the microcontroller is receiving the zero crossing detection signal. Let me show you its part number. As you can see, this is its part number. It is completely different from the outdoor unit IC, which is why its operation is also different. Pin number 1 is the 5-volt supply. This IC will operate only if it receives 5 volts, otherwise it will not work. Now, let's check pin number 3 and pin number 1. We will use pin number 3 as the ground reference. Here is pin number 3, and pin number 1 is connected to this point. As you can see, this point here belongs to pin number 1. There should be 5 volts DC here. As you can see, the 5 volts are reaching the pin properly, which means this hybrid IC should be operating. Next, another important voltage required is the 5-volt supply for the microcontroller. If this voltage is missing, the microcontroller will also not operate. So let's check it. The operating voltage for the microcontroller is available on pins 19 and 20. Here you can see capacitor C24. We will measure the voltage across this capacitor because one side is connected to the 19 and 20 pins, while the other side is connected to ground. Let's check both sides. There should be 5 volts here. At first, it looks like 5 volts are not present. Let's use a different ground point. Sorry, the meter is currently set to AC voltage. We need to switch it to DC voltage. Now, let's check across the capacitor again. As you can see, 5 volts are reaching this point. We are measuring across capacitor C24. One side is connected to pins 19 and 20 of the microcontroller, and the other side is connected to ground. As you can see, the 5-volt supply is stable here, so this section is working properly. Another important voltage to check is on pins 56 and 59. As you can see, this is capacitor C19. We will measure the voltage across this capacitor. There should also be 5 volts here. As you can see, 5 volts are present, which is perfectly okay. Here is pin 56, and here is pin 59. These two pins are connected together, which is why they join at the same point. These are the AV analog voltage pins. This is where the analog signals are converted into digital form, and the digital signals are also processed into analog form by the microcontroller. These AV voltages are very important because the analog signals first enter here. The microcontroller converts them into digital form for processing, and then the processed data is converted back into analog signals to operate the rest of the system. So this check is also complete. Next, look here. Capacitor C19 is also connected to pin 60, while the other side is connected to ground. This confirms that the required voltage is reaching this point, so this part of the test is complete. Now, look here again. Pins 19 and 20 are the positive supply, while pins 17 and 18 are the ground pins. We have already verified both of them through capacitor C24, so that test is also complete. Next, we will check pin number 10. As you can see, this mark indicates pin number 10. We should also have 5 volts here because these are the reset voltage. We will use pin number 24 as the ground reference and check the voltage on pin number 10. As you can see, 5 volts are present. The reset voltage is correct, and the IC is receiving it properly. This means the microcontroller should be operating, but it is not. After this, the next important voltages to check are related to its heartbeat. As you can see, this is its heartbeat, which means this is the crystal. If a person's heartbeat stops, that person cannot stay alive. In the same way, the crystal acts as the heartbeat of the microcontroller. It generates the clock pulses, and these pulses allow the microcontroller to perform all of its functions. If the voltages here are not correct, this can also cause a problem. So let's check the crystal. Its center pin is ground. One side is the input, and the other side is the output. Now let's see what voltages are present on both the input and output, because when the crystal is installed in the circuit, both sides normally show approximately half of the supply voltage. Since this is a 5V microcontroller, we should see around 2.5 volts on both the input and output pins. Let's check it with respect to ground. As you can see, the voltage is 1.143 volts. This is not correct. These voltages are abnormal. Now let's check the other pin. This will also help us determine which side is the input and which is the output. As you can see, the other pin is also showing 1.123 volts. This is also not correct. There is clearly something wrong with these voltages. It is possible that the crystal is internally shorted or has some other fault, which could be causing this issue. So, I will turn the power off. The power is now off. Next, we will remove the crystal, because it is not producing the correct voltages. Let's remove it. As you can see, its reference designator is X1. In any microcontroller circuit, the crystal is usually marked as X, X1, X2, or something similar. We will remove it first. And now it has come out. Here it is. The crystal has been removed. Now let's check its part number. The part number is printed on top of the crystal. This crystal operates at 8.00 MHz. We will install another crystal in its place. However, before doing that, we must first check whether the input voltages reaching the crystal are correct or not. This is very important, because if the input voltages are not correct, even after replacing the crystal, we may still get the same readings on its input and output pins. Now, I will power the system again. The power is now on. Let's check it. The center pin is ground, so we will place the black probe on the ground pin and check each sign to identify the input and output. As you can see, this side is still showing 1.6 volts. Now, let's check the other side. On the second point, it is still showing 1.16 volts, which is not correct. One side should not have any voltage, while the other side should have 5 volts with respect to ground. Let me check again using a different ground point. I will take the ground from another location and measure it again. As you can see, the readings are still the same. The voltage is around 1 volt and it is fluctuating. It is not stable. On the other point, the reading is also the same. The voltages here are not correct. One point should have 5 volts and the other point should have no voltage on the output side. But both points are showing voltage. First of all, we will replace the crystal. Although the voltages coming from the microcontroller are not correct, let's replace it once and see what happens. Here it is. This is also an 8 MHz crystal. It has no polarity, so you can install it in either direction. It will work correctly either way, because one side automatically becomes the input and the other becomes the output. Now, after replacing the crystal, let's see what voltages we have. We will use the center pin as the ground reference. As you can see, nothing has changed. The voltages are still exactly the same. Let's check the other side as well. It is also showing the same reading. There should have been 5 volts here, but instead, it is showing only 1.1 volts. The voltages for this crystal are coming from here. As you can see, they come from pins 13 and 14. Both of these voltages are supplied directly by the microcontroller to these two pins. It seems to me that the microcontroller is internally shorted, which is why these voltages are being divided equally. Because of this, the microcontroller is not starting, since its heartbeat is not working. As a result, the microcontroller cannot operate. The 5-volt signals originate from inside the microcontroller, come out to the crystal, and then return back into the microcontroller from here. At this point, we cannot determine which pin is the input and which is the output, because both pins are showing the same voltage. If the signal were coming from one side and going to the other, we could identify the input and output. But since the voltages are identical on both pins and the signal is not going anywhere else, this indicates a major issue. This is not normal, because these pins are not being supplied through pull-up resistors. Instead, the voltages are coming directly from the microcontroller itself. It appears that the internal circuitry connected to these two pins has become shorted, which is likely why the microcontroller has stopped working.
Click on the left or right thumbnail to watch our next videos. And subscribe. Thank you.